Okay, hello. We're going to work our way through some more problems from this sequences in series packet. Here we go, we're on page 3 now, and here's what it says. This number 12 says, find x if the sequence AXB is arithmetic. Okay, I already did this in a previous video. So, what is this number x such that AXB is an arithmetic sequence? Well, if it's an arithmetic sequence, the definition of arithmetic sequence is that there is a common difference between a term, or the difference between a term and a previous term is the same for the whole sequence. So I conclude that x minus a, the gap between x and a, has to equal the gap between b and x. And therefore, what is x? Well, I can add x to both sides, so I get 2x is a plus b, and so x is a plus b over 2. Okay, and this thing, a plus b over 2, is called the arithmetic mean. This is what it says on the packet. Okay, so then we may also construct the geometric mean. What's the geometric mean? The geometric mean of two numbers a and b is the number x between a and b such that AXB forms a geometric sequence. So now, if this second sequence here is understood to be geometric, then what must be true? The ratio between a term and the previous term has to be the same. So the ratio between x and a is the same as the ratio between b and x. And if that's true, then x squared is ab, and so x is root ab. And this number is called the geometric mean. Okay, I think it's possible, well, you've certainly seen arithmetic means before. That's just what you call average. And even geometric mean, I believe you saw in geometry, although you probably didn't have it explained to you why it was called the geometric mean. You should think of it as really being about geometric sequences. But there are some geometric applications. This is kind of a different use of the term geometric. There are some geometric applications of the geometric mean. It arises in geometry a lot. Okay, so everything I'm about to do on this packet is stuff that I'm pretty sure you did this. I mean, it's sort of in the basic geometry curriculum, but okay, you know, it's been a while. So here we have a right triangle. A generic right triangle, ABC, with a right angle at C, and the sides of the triangle labeled, you know, little a, little b, little c, by convention as the lengths of the opposite sides of the triangle, opposite the angles. And then we drop a perpendicular from C to D, and we let that height be h. Okay, so this is the kind of famous altitude to the hypotenuse of a right triangle kind of theorem. And all right, I walk you through all the steps of this right now. So your first task was to prove that triangle ADC is similar to triangle CDB, which is in turn similar to ACB. Why is that true? Well, it's convenient to introduce some angles into this argument. Okay, so let's call this angle alpha, and let's call this angle beta. Alright, well, what do I know about alpha and beta? I know that they add up to 90, because alpha and beta and the right angle makes triangle ABC, and they're 180 degrees in triangle ABC. So alpha and beta are complementary. They add up to 90. Well, if that's the case, then what's this angle here? Well, it must be alpha, because that's a right angle, and so these two angles are also complementary. So having defined this angle as alpha and this angle as beta, I now conclude that this angle is alpha, and similarly this angle has to be beta, either because these two add up to 90 because that's a right angle, or alternatively you can look at this triangle, it's also a right triangle. Okay, so this now is just done, right? ADC, so ADC, this is like kind of alpha 90 beta, is similar to CDB, so that's alpha 90 beta, is similar to the original triangle, alpha 90 beta. Alright, so the big theorem here is that when you drop a perpendicular from the right angle to the opposite side, the hypotenuse, then you split the original right triangle into two smaller right triangles, each of which is similar to the original triangle and hence they're similar to each other. Okay, and now the rest is kind of easy. The next thing you were asked to prove is that h is the geometric mean of x and y. What are x and y? They are the pieces that the hypotenuse was split into when you drop that perpendicular. Okay, so I'm looking for a relationship between h, x, and y, and well, I use the fact that these two triangles are similar. So I just set up a proportion. You know, the side opposite alpha is to the side opposite beta, so h is to x, or long leg is to short leg, you might say, in the small triangle, as long leg is to short leg in the medium triangle. It's probably better to talk about angles. I think this is a better way to do it, but anyway, I think you get it. Side opposite alpha is to side opposite beta, as side opposite alpha, y, is to side opposite beta, h. Okay, and of course, now you just do some algebra. H squared is xy, and therefore h is root xy. So this can be summarized as the altitude to the hypotenuse of a right triangle is the geometric mean of the pieces of the hypotenuse that the altitude cut the hypotenuse into. Okay, good. This one, it's possible that you never did before. Number 3 says, show that B is the geometric mean of x and c. Whoa. Okay, so I'm looking for some kind of relationship between B, x, and c. What is the relationship between B, x, and c? Well, in the little triangle, B is the hypotenuse and x is the side opposite beta. In the big triangle, C is the hypotenuse and B is the side opposite beta. But since this little triangle is similar to the original triangle, then we can once again set up a proportion. So I can say, well, it doesn't matter how you do it, right? The hypotenuse, B, in the little triangle is to the side opposite beta, x, as the hypotenuse of the big triangle, triangle ABC, C, is to the side opposite beta, which is B. Boom. And so B squared is xc, and so B is root xc. Okay, that's kind of exciting. Now we just do it again with number 4 is kind of the exact same thing. A is the geometric mean of y and c. So A, y, c. I need a relationship between A, y, and c. Well, okay, I think I got this now, right? What is A? On the one hand, it's the hypotenuse of the medium triangle. On the other hand, A is the leg opposite alpha in the original triangle. So once again, I can set up a proportion. A is to y. So now I'm saying, well, hypotenuse is to side opposite alpha in this triangle, as hypotenuse C is to side opposite alpha in the original triangle A. And so indeed, I get that A squared, A squared equals CY, and so A is root CY. Okay, and finally, we have this statement which just says, hey, just like prove the Pythagorean theorem. Whoa, that's kind of crazy. This is actually one of the ways to prove the Pythagorean theorem. This is how some geometry textbooks actually kind of walk you through a proof of the Pythagorean theorem in this exact way, as an application of this figure. Well, okay, we just take parts 3 and 4, right? What do I know in part 4? I know that A squared is CY. And in part 3, I know that B squared is XC. So I just add them up. And if I add this up, I get that A squared plus B squared equals C times X plus Y. But of course, X plus Y is C. So this is just C times another C. So A squared plus B squared equals C squared. So this is like a legit way of proving the Pythagorean theorem. Okay, good. That was page 3. Let's keep on going here. Let's go to page 4. Well, on page 4 we have some kind of like open-ended, not open-ended, but problems that require you to do some kind of independent thinking. So give an algebraic or a geometric proof that the arithmetic mean of two positive numbers is greater than or equal to their geometric mean. Oh boy. Okay, what is the arithmetic mean of two numbers? It's a plus b over 2, and I am supposed to show that the arithmetic mean is greater than or equal to the geometric mean. So in other words, this is what I need to prove. I need to prove that a plus b over 2 is greater than or equal to root ab. Okay, how are we going to do this? Well, hopefully I've convinced you over the previous week or so that whenever you have these kind of complicated proofs, the thing to do is just sort of work backwards. So let's work backwards. This is what I'm trying to prove. So what would have to be true in order for this thing I'm trying to prove to be true? In other words, let's simplify this. Okay, one thing we could do is move the 2 over to the other side. So this is true if and only if a plus b is greater than or equal to 2 root ab. And this square root is kind of just begging you to square it because, that's just what the definition of the square root is. It's the thing which when squared is ab, and so to get at the content of this expression in some kind of way, I need to square both sides. So let's do that. If I square both sides, I get a squared plus 2ab plus b squared, and on the right hand side I get 2 root ab times 2 root ab is just like 4ab. Now I see, if I bring everything over to one side, I get a squared minus 2ab plus b squared is greater than or equal to 0. And here's the thing. That's just true. Because this is a perfect square trinomial, and that is a minus b is greater than or equal to 0. And so it's just a fact of numbers that when you square something, then it's just greater than or equal to 0. Therefore, this statement is just true. And now the smooth thing to do now, if you're one of these kind of cool people, is just throw in a couple of double arrows. This avoids us having to sort of rewrite things. In other words, the claim I'm making here is that every single step along the way was perfectly reversible. So in other words, this thing I'm trying to prove is true if and only if this is true. In other words, I can go from here to here and from here to here. Both are true. I think that's true, right? You can multiply both sides by 2, you can divide both sides by 2. From here to here, I square both sides. Well, squaring both sides is also legitimate as long as everything is positive, which it is. So I can go from here to here, but also backwards. And from here to here, I just subtracted 4ab from both sides, and here I just factored. In other words, since this is true, my original statement is true also. So, okay, done. Alright, now there was some reference to a geometric proof. It is possible to do this thing geometrically. And, okay, this assumes that you remember a certain theorem from geometry, and it's the theorem that you really should know about angles inscribed in a semicircle. So if this is a circle with center O, and you just take any point, so let this be like A, B or something, and then if you take any point x whatsoever on the semicircle, then it is a fact that AXB will be a right angle. Why is that? Well, how can we show this? Well, one thing to do with circles is to connect the radii, and so if I connect that line x to O, then what do I have here? Well, I have kind of like a bunch of equal segments now. Each of those are radii. So okay, I guess let's label some of the angles here. So let's label this angle alpha, and let's label this angle beta. Well, now I see, right? This is an isosceles triangle, so this is alpha, but this is also an isosceles triangle, so this is beta. And now, alpha plus beta has to add up to 180, because it's a triangle. So if 2 alpha plus 2 beta is 180, then that means that alpha plus beta is 90. And that proves that this is a right angle. Okay, so extremely important and basic math fact is called Thales' theorem. It's one of the earliest geometric facts kind of ever proven that we have evidence of. And what it says is that that this is always a right angle from one endpoint of a diameter to a point on the circle to another endpoint of the diameter. Okay, why should I care about that? Well, if I then drop a perpendicular from this, then that's the geometric mean of the two pieces. And so, here is the sort of geometric proof, the geometric proof that the arithmetic mean is always greater than or equal to the geometric mean, considers a semicircle. So now I'll redraw it here. We consider a semicircle composed of, looks so bad, composed of two segments A and B. So perhaps let this be, no, I guess I should, let this be A and let this be B here. So in other words, let the diameter of your circle be A plus B. And now construct a point up. And this point, being on the circle, will make this a right angle. And therefore, I have now a sort of visual consideration or something. I've constructed a diagram in which this is root AB. So the geometric mean of two numbers should perhaps be thought of, via the previous page, as the altitude to the hypotenuse of a right triangle. It's the length of the altitude to the hypotenuse of a right triangle in which the hypotenuse has length A plus B. So this is kind of a follow-up on the previous page. If someone asks you to sort of draw a picture of the geometric mean, this is kind of the picture that you draw. Now, putting the entire thing in a semicircle is not an obvious thing to do, and maybe I should have done that kind of second. Okay, based on the previous page, drawing at least the triangle is maybe a good idea. But then, of course, what is A plus B over 2? A plus B over 2 is sort of just the average of A and B. So it's the midpoint of the segment whose length is A plus B. In other words, A plus B over 2 is the radius of this circle. And thus, I'm done. Because if this is the arithmetic mean, is the radius of the circle, and the geometric mean is the height from a point on the circle back down to this diameter, then this shows that in fact the arithmetic mean is always greater than or equal to the geometric mean, because root AB is kind of like a half chord of the circle, and a half chord can be at most a radius. So the length of a half chord in a circle is always less than or equal to the radius. That's kind of what this is saying. Okay, so that was kind of exciting. Let's do the next problem, which is also just sort of, I want to call it like remedial geometry or something. That's kind of an obnoxious thing to say, because this is either, this is something that you definitely learned and that, you should have been able to do once upon a time, but it's been a while, so it's like review. Here we go. Consider a circle with radius 6. Find A, the area of the inscribed equilateral triangle, and B, the area of the circumscribed equilateral triangle. Show that the geometric mean of A and B is the area of the inscribed regular hexagon. Oh boy. Okay, so I have sort of three shapes that I need to draw. And how am I gonna do this? I guess the smart thing to do would be to erase everything now. So I have a circle of radius 6. I want to consider the inscribed equilateral triangle, the circumscribed equilateral triangle, and the inscribed regular hexagon. Okay, so let me draw three circles. Circle. Gotta be kind of careful here. Circle. circle, circle. Those all look reasonably equal to each other. Okay, great. What am I supposed to be drawing again? Well, the inscribed equilateral triangle, so that's this one. So it looks like this. And alright, some kind of background knowledge here on equilateral triangles. Every equilateral triangle has a point. In fact, every regular polygon has a point called the center, and the center is equidistant from all of the vertices. So that and that and that are all 6. So 6, 6, 6. Yeah. Okay, therefore, to me, so my goal is to find the area of that blue triangle. To me, the simplest thing to do is to just find the area of like one of these triangles and then multiply by 3. So how do I find the area of one of these 3 triangles? Well, I guess I need to know the base and the height, neither of which I know right now. So from here, I'll drop a perpendicular. Now, you know, these 3 triangles are all equal to each other because these 3 angles are all, well, they just are. So by SSS, I suppose, right? Because by definition of equilateral, blue, blue, blue is all, they're all the same. And of course the radii are all equal. So of course these 3 angles are all equal and they're all 120 because they have to add up to 360. Therefore, if I drop a perpendicular, since this triangle is isosceles, then it makes this the angle bisector. So that's 60 and that is 30. Okay, so this whole thing, by doing a bunch of sort of geometry, I conclude that this is a 30, 60, 90 triangle. And, well, if this is 6, then what's this? This is going to be just half of that. So by 30, 60, 90 triangle ratios, every 30, 60, 90 triangle is kind of half of an equilateral triangle, in fact. So that's just 30. And the side opposite 60 is always square root of 3 times as much as the side opposite 30. So this is 3 root 3. And therefore, to me, the simplest way to find the area is to say, okay, what's the area? Well, it's going to be 3 of these triangles. And what are the area of each of these triangles? Well, each of them is 1/2 the base, which is going to be 6 root 3, times the height, which is going to be 9. I guess that's what I did. Oh no, sorry. The overall, that seemed wrong. The height is 3 because I'm just looking at kind of one of these triangles here. So just kind of like this black one. So 1/2 base is 6 root 3, height is 3. Okay, so what happens when I multiply all this stuff together? I think that becomes 27 root 3. So this is 27 root 3. Okay, great. Next problem. Find the area of the circumscribed triangle. So what does that look like? Well, it's the triangle formed, the equilateral triangle formed by line segments which are tangent to the circle at these 3 points. And okay, what can I say about this triangle? Well, this point is then the inscribed circle. This point is like the incenter. You know, in fact, it's just the intersection of the angle bisectors. So okay, that's like 90, and that's 90, and that's 90. So it's kind of this type thing. But anyway, the logic is kind of the same, which is I need to find out what the area of just one of these triangles is, and that will be sort of good enough. So I do this, and once again, goal, find the area of like just that green one there, and then multiply by 3. And what do I know about this figure? That this circle has radius 6. So these angles are all equal to each other, so this right here is 60 degrees, and this is 30. Okay, if you crave like a deeper explanation of this, then you can just know that okay, for a given triangle, this point is in fact just the incenter. So it really is just the angle bisector. Okay, let's not go into this too much. That's 60. That's 30. What's the area? Well, the area is going to be, there are going to be 3 of these triangles, and each one has area 1/2. The base, well, what is the base? If this is 6, then the side opposite 60 is going to be 6 root 3, and I think that's all I need to know, actually. So this is going to be 1/2. The base is 12 root 3, 12 root 3, and the height is 6. So I think, let's see, what do we get here? 6, 6, 6, so that's 36 times 3. That's 108 root 3. I think that's right. Okay, and finally, what happens if I inscribe in this circle a regular hexagon? So let's see if I could do this in a good way. It seems relatively fine. Okay, so boom, boom. So here we have some kind of properties of hexagons. Well, once again, every regular polygon has a center, which is equidistant from all the vertices. So, oh man. So that's 6, and that's also 6. But in a hexagon, this central angle here is 60 degrees. So because there's just 6 of them. So, I mean, I can kind of draw the rest of them if you want, but there are 6 triangles, each of which is congruent, because they all have radius 6, so all these purple segments are congruent, and all the blue ones are as well, so we have 6 SSS triangles. They're all isosceles, so these 2 angles are equal, but also that's 60. Well, if that's 60, then there's only 120 left to go around to this. Okay, so math fact, these 6 triangles in a regular hexagon are all equilateral. And if that's the case, then I can once again just find one of them by dropping a perpendicular. If that's 6, then that means that's 3, and that's 3 root 3. So, the area of this regular hexagon is 6 now of these triangles, each of which is 1/2. The base is 6, and the height is 3 root 3. Cha-cha-cha. Okay, so what's all that? I guess that's 3 times 3 times 6, so 9 times 6, 54 root 3. Okay, so this is kind of like the long way or something to do this problem, which is just totally fine. Is it true that 54 root 3 is the geometric mean of 27 root 3 and 108 root 3? Well, the question just becomes, is 27 root 3, comma, 54 root 3, comma, 108 root 3, is this a geometric sequence? Well, let's find out. What do I have to multiply 27 root 3 by to get 54 root 3? Well, I think it's just, the answer is just 2. And if you multiply by 2 again, then boom. So in fact, yes, these 3 numbers are in a geometric progression, and therefore the problem's over. Okay, that is sort of 2 pages down, some maybe like many more to go or something. Let's just keep on going. Whew. Alright, page 5. Page 5 is just a whole bunch of little problems about various recursive sequences. Okay, let's go. Maybe this was a little bit overkill, I don't know, let's do it. Number 17. They tell me that the first term is 6, and they tell me that the nth term is the previous term plus 4. Okay, so this is really just kind of easy, right? What does that mean? Well, the first term is 6, the next term is 10. I just keep adding 4. Okay, this is just silly. So 14, 18, 22. This is the third, fourth, and fifth term. All right, that's one down. That was a nice, easy problem. 18. Oh, this is getting exciting. The first term is 2. The second term is 4. And the nth term is the sum of the two previous terms. So this is kind of like the Fibonacci sequence, but with different initial conditions. Instead of starting 1, 1, this starts 2, 4, but otherwise it follows the Fibonacci pattern. Okay, so that's pretty fun. So this is 2, 4. What's the third, fourth, and fifth term? Well, the third term is going to be the sum of the previous two terms, so that's 6. The fourth term is the sum of the previous two terms, so that's 10. The fifth term is the sum of the previous two terms, so that's 16. Alright, that was pretty chill. 19. The first term is 1, and, ooh, this is exciting. The nth term is, this is a more complicated pattern. It's the previous term plus 2n minus 1. Okay, great. Well, let's do it. So the first term is 1. Now the next term is what is it? It's going to be 1 plus, well, n is 2 now, right? So maybe I should just write this down, right? And this is when n is 2, this is when n is 3, this is when n is 4, and this is when n is 5. So, boom, boom, let's go. Well, when n is 2, I'm supposed to take 2 times 2, so 4 times 3, I'm supposed to add 3 to the previous term. So that's 4. But when n is 3, I'm supposed to add 5 to the previous term, so that's 9. When n is 4, I'm supposed to add 7 to the previous term, so that's 16. And when n is 5, I'm supposed to add 9 to the previous term, so that's 25. And actually that's just the perfect squares. So actually kind of, we should have seen that coming, right? Because we already knew that the perfect squares, in fact, had this property that their gaps were the perfect squares had this property that their gaps were the odd numbers, right? They go up by the odd numbers every time. Go up by 3, go up by 5, go up by 7, go up by 9. So if I was being smart, I could have recognized that pattern right away. Okay, more 20. What's 20? Give a recursive definition for each sequence. Okay, so here this is just pattern recognition. This is the kind of thing I said I didn't like on the first day, but it's still kind of a skill. What do all these numbers have in common? Describe the pattern and define it recursively. These numbers are all 1 less than powers of 2. So it actually might be faster to give a explicit definition, but anyway, they asked for a recursive definition, so this is 1. How do I get from 1 to the next number? Well, I guess I can add 1, multiply by 2, subtract 1? Is that what I did? Yeah, so it's the previous... Yeah. It's just the... Yeah, okay, so here it is. It's you just multiply by 2 and add 1. So it's just 2... the previous term plus 1. That's really all I have to say about that. Alternatively, there was another way you could have done it. You could have said it's like... I think this also works. That you can say it's going to be the previous term plus 1 times 2, and then minus 1. Of course, that actually turns out algebraically to be the exact same thing. But this to me seems maybe like a more honest answer because how are you getting... Well, I'll just leave that alone. Problem done. 21. 21, again, we have some sequence. 1, 3, 6, 10, 15, 21. Ooh, I know these. These are the triangular numbers. So this is 1, this is 1, 2, 3, this is 1 and 2 and 3, 15 is 1 and 2 and 3 and 4, and I'll stop drawing now. So these numbers should maybe kind of jump out at you as being significant. They are each the sums of all the numbers up to that point. So actually it's quite simple. Once again, for this problem it might be easier to just give a explicit definition. The explicit definition is going to be n plus 1 over 2. I think I did that right. By the time I get to the fifth term, it's 5 times 6 over 2, yeah. But anyway, that's while that's correct, that's not actually what the problem wanted. The problem wanted you to give it recursively. So to give it recursively, you say, okay, the first term is 1, and each term I get by, well, I just add on another row of this triangle, right? So when I'm on the third term, for example, I should add 3 to the previous term. When I'm on the fourth term of this sequence, I should add 4 to the previous term. So it's going to be the previous term plus n. Okay, cool. Next, 22. 1, 2, 6, 24, 120, 720. Okay, these numbers are also famous. These are the factorials. So how do you get from one of these to another? You multiply by something, right? So here you multiply by 2, here you multiply by 3, here you multiply by 4, then you multiply by 5, multiply by 6, etc. Okay, so I'll just do this one. The first term is 1, and each subsequent term is the previous term times n. Yep. To get to the third term, I multiply 3 by the previous term to get to the fourth term, etc. Okay, good. 2 more from this page 5. Here we are, number 23. Here's what they tell you. The first term is 3. The second term is 5. And then the nth term is the previous term minus the term 2 back. Whoa, that's kind of crazy. Okay, well, let's just begin. So, first term. Maybe I should write this out kind of carefully. First term, 3. Second term, 5. Third term is 5 minus 3, which is 2. Fourth term is 2 minus 5, which is negative 3. Okay, fifth term is negative 3 minus 2. That's negative 5. Am I doing this right? Apparently I am. The sixth term is negative 5 minus negative 3. That's negative 2. The seventh term is negative 2 minus negative 5. That's negative 2 plus 5. That's 3. Oh. And the eighth term is going to be 3 minus negative 2, so that's 5. Aha! And now this crap is just going to start repeating again. And so I think I've cracked the code, right? It just kind of goes like 3, 5, 2, negative 3, negative 5, negative 2, 3, 5, and then it's just going to keep repeating again. So this is going to repeat with a cycle of 6. This is the kind of thing you're supposed to figure out. And therefore, the question is, what is the 1000th term? So I need to know what's up with that 1000th term. Well, what is 1000 anyway? I guess 1000 is like 996 plus 4. And 996 is a multiple of 6. Therefore, we say, if this is repeating every 6, that I really need to consider like 1000, mod 6. And 1000 mod 6 is 4. I think everyone knows that stuff. So this is therefore going to be, the 1000 term is going to be the same as the fourth term. So then the answer to this problem is just negative 3. Okay? Woo! That's like a nice little middle school math team challenge problem. 24. Give the first 10 terms. Whoa. Oh, here I kind of cheated a little bit once I got in control of things. Give the first 10 terms of the sequence. Okay. So T1 is 4. T2 is 8. And what am I supposed to do next? Ooh, the nth term is the ratio now between Tn minus 1 and Tn minus 2. Okay, let's go. And then once again, I want the thousandth term, yeah. So the first term is 4, the second term is 8. The third term is the ratio between 8 and 4, which is 2. The fourth term is the ratio between 2 and 8, which is 1/4. The fifth term is the ratio between a fourth and 2. 1/4 divided by 2 is 1/8. The sixth term is the ratio between an eighth and a fourth, which is half. The seventh term is the ratio between a half and an eighth, which is 4. And the eighth term is the ratio between 4 and a half, which is 8. Okay, so I could keep going. I mean, they said do the first 10, but I don't really think I need to, because I got this now, right? 8 divided by 4 is 2, 2 divided by 4 is 1/4. So this thing really is going to keep repeating. Also, every 6. Here, there's kind of like a line, and this thing is basically just going to go 4, 8, 2, a fourth, an eighth, a half, 4, 8, 2, a fourth, an eighth, a half, forever and ever and ever. And so, I think it's the same thing, right? The thousandth term is also going to be equal to the fourth term for the exact same reasons. And so the answer to this problem is 1/4. Yeah. Woo! That was great. Okay, let's do page 6 of this packet, and then maybe kind of end this video. Okay. So. Page 6 of the packet. Oh yeah, this crazy problem. Okay, so goal, we want to know the number of diagonals that can be inscribed in a polygon. Well, this is very exciting. Suppose you've never heard this problem before. How many diagonals does a triangle have? None. So that's 0. How many diagonals does a quadrilateral have? 2. How many diagonals does a pentagon have? Well, maybe I should use a different color. A bunch, I guess. So here's 1, 2, and then this is going to be 1, 2, 3, 4, 5. That's pretty exciting. And, you know, etc., etc. So the goal of this problem is to find the pattern, find the formula for the number of diagonals. Okay, and I stopped even counting here. Whoa, kind of just zoned out for a second there, did some garbage. And what am I missing? That one, and that one, and I don't even know if that's right. I think I'm missing one more. That one. And now we are looking good. Okay, so, right. So I got this problem from a textbook, and they walk you through this kind of particular, oh, so by the way, how many are there here? Man, I don't even know, except I do, that there are going to be 9 here. Okay. Yeah. So this problem walks you through a certain technique for coming up with this formula. And okay, here's what it says. First, it shows you a generic hexagon, and it has you count the number of diagonals. And the answer is that there are 9. That's what it says in the paper. So now, here's what we kind of want to do. We want to say, take this hexagon. Let me try to redraw it here. So cha, 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 cha. So there's my hexagon, say. And okay, as we said, there are 9 diagonals. Let's draw them all carefully and count them. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Great. Okay, well now, says the problem, imagine pushing out one side of the hexagon. So consider this side. Dissolve that side, And so, and now you have sort of a 7th point, which is now chilling out here. And, well, what can I do with that 7th, new 7th point? This is the 7th point. What we're now reflecting upon is the number of extra diagonals you get by adding an extra side. So if I now know that there are 9 diagonals in a hexagon, how many new diagonals do I get? Okay, well, how many do I get? From this new point, I can draw some more diagonals. How many? Well, to this point is going to be a new diagonal. To this point will be a new diagonal. Wait, what? Oh yeah. To this point there is a new diagonal. To this point there is a new diagonal. And there's kind of like one more new diagonal, which is that the old thing which was a side length is now a diagonal. Okay, so I claim that the answer for a 7-gon must be 14. But more to the point, it seems that 5 additional diagonals are possible. 1 to each of these vertices, so I'll circle them, 1, 2, 3, 4, and then the side that I kind of broke down became itself a diagonal. Okay, and why were there 4? I guess there were 4 because this 7th point, well, you can't draw a diagonal from this point to itself. Neither can you draw a diagonal from this point to the 2 adjacent points. So okay, so first of all, the first observation is that, let's call this D7, the number of diagonals. I think that's what the packet tells you to call it, I can't remember. D7 is just D6 plus 5. But to really understand, and maybe, you know what, maybe I'll just finish this problem off right now. Because I'm speaking of this sufficiently generally that I think I can now state the full general recursive rule. And the full general recursive rule is that the number of diagonals in an n-gon is equal to the number of diagonals in the previous n-1 gon. In other words, by thinking of this now as not the 7th point, but as the nth point, then I can say that the number of diagonals this will have were the old number of diagonals plus the new diagonals added. And how many new diagonals do I get to add? Well, I get to add 1 connecting the 2 points that used to be a side length, but I kind of busted out from that side. And then, how many of these other diagonals? Well, these other diagonals are to each of the vertices that aren't myself or my 2 neighbors, because those are sides. So from here to here is a side of the polygon, from here to here is a side of the polygon, and then from here to every other vertex of the polygon is a diagonal. Therefore, if this is an n-sided polygon, there are going to be n minus 3 of these diagonals. And so I take the previous number of diagonals, I add n minus 3 new diagonals from the new point to all of the other points except for the 3 nearby, and then even plus 1 more because of this new diagonal, this new side length that gets converted into a diagonal. And so the general recursive rule is that the number of diagonals in an n-gon is the number of diagonals in an n-1 gon plus n minus 2. Okay, having done that, I would like to say that this problem kind of sucks, because this is just not a good way of doing this at all. There's a much more elegant and simple way to do this problem, and you get a better formula, and it's like kind of less effort and more clear and everything. So, okay, here is a pentagon. Let's just count directly the number of diagonals that it has. Well, let's see what's going on. From any vertex, we have a diagonal to every other vertex. So there's the diagonal, and there's a diagonal, not every other one. Everyone besides the adjacent ones and besides itself. And now we just kind of keep doing this. Okay, hold on, I lost my train of thought for a second. But that's the total number of diagonals. So the question is, how many are there? Well, let's consider how many diagonals there are at each vertex. And the answer is, at any given vertex, there will be 2 diagonals. Why 2? Because there are only 2 sort of eligible other vertices that I can draw diagonals to. That one and that one. Okay, and so you might be thinking, well, this is a pentagon. So there are 5 vertices, and at each vertex there are 2 diagonals. So therefore there are 10 diagonals. But that's not quite right, because by looking at what's going on at each vertex, so here I count 2 diagonals, here I count 2 diagonals, here I count 2, here 2, here 2. But now I've overcounted by a factor of 2 because I've counted every diagonal twice. Every diagonal connects 2 vertices, and so you have to kind of divide by 2 to get that the right answer is 5. That was kind of a bad example. Let's maybe go to hexagon. This is kind of better. So now, so here's my hexagon. And, okay, well, it's the exact same logic again, right? Let's draw the diagonals. How many diagonals can I draw from any given point? Well, from any given point, there's going to be diagonal here, here, and here. Why 3? Because there are 6 vertices, but I can't draw a diagonal to myself, neither can I draw a diagonal to either of my 2 neighbors. So it's always going to be n minus 3. And, okay, from this vertex, there are also 3 diagonals. 1, 2, 3. From this vertex, there are also 3 diagonals, but one of them has already been accounted for. So 1, 2, 3. From this vertex, there are also 3, but one of them has already been accounted for. So 1, 2, 3, and now 1, 2, 3. In other words, at every vertex of this hexagon, there are going to be 3. Diagonals. So I have 6 vertices times 3 diagonals at each vertex. But once again, I need to divide by 2 because I've double counted every diagonal, and so the answer is 9. Alright, so finally, in the general case, if this is an n-gon, then how many diagonals are there at any given vertex? I think I've argued that the answer is that there are n minus 3 of them. And so, looking at one vertex at a time, I should say that there are n vertices in the n-gon. There are going to be n minus 3 diagonals from that vertex, and that counts every diagonal twice. And so we divide by 2. Sorry, I paused for a second there, but I think we're good. Yeah. So this is just the answer to this problem. It's n minus 3 over 2. Is that just right? N squared minus 3n over 2. N squared minus 3n. Sure it is. Yep, that's just the right answer. Okay, so I think this is kind of just like a better formula for this thing. It's just, yeah, okay. Good. Last problem of this video is going on forever. So, yeah. Erase all this. Leave up the pretty picture. Let's do this last little problem. Find the sum of all multiples of 3 between 1 and 1,000. So, sum of all multiples of 3 between 1 and 1,000. Okay, this is kind of like similar to something we did on the front. So what's the first multiple of 3? Well, 3. And then we're 6 plus 9 plus, and then what's the last number? Which is the multiple of 3? Well, 999 is a multiple of 3, so there you go. Alright, so actually this whole problem just boils down to what is 3 plus 6 plus 9 all the way up to 999. Okay, so the very organized way to do this would be to figure out, what term is this? So if the first term is 3 and d is 3, then, the nth term will be the first term, 3, plus n minus 1 3 times. and then that's supposed to be 999. This is kind of a little bit over the top, but okay, anyway, let's just finish it off. So that's 333, so n minus 1 is 111, so n is 112. You could practically have done this in your head. Ultimately, all I'm doing is I'm saying, all right, all the way from 3 to 999, how much did I jump? Answer, I jumped by 996. Well, if I jumped by 996, and I'm jumping by 3 every time, then I must have, sorry, lost my train of thought for a second. Subtract. So wait, this was just wrong. That's just a bunch of garbage. 993 minus 3 is 996. Divided by 3 is 332. And therefore n is 333. Good thing I thought to do this problem 2 different ways. Yeah, this is the my conclusion. This time I think I'm right. Is that this is the 333rd term of this sum. And okay, that just makes sense because if there are 333 terms and I skip by 3 every time, then by the time I get to the 333rd term, I have made 332 jumps of size 3, and that's a total change of 996. Okay. Woo, good. Great. So basically, now what is there to say? Well, I want the sum. I want the sum of them all. Probably the simplest thing to do here is just to do first term. Yeah. So this is going to be the average term times the number of terms. So the average. So this is one of the kind of formulas that if you want to. This is one of the ways of adding up all the terms of an arithmetic sequence. That it's the average term times the number of terms. Okay, so if I want the sum of the first 333 terms, then this is 333 times what is that? 1002 over 2. Okay, so this is just some big number. I don't really feel like doing this. 333 times 501. Maybe I'll just leave it like that. Yeah, I'll just leave it like that. That's the right answer. Okay, good. That was page 6 of this packet. Maybe that's all I will give you, in fact, for, well, I don't know. We'll see. Bye.